Hello. Here we'll discuss a crypto system based on elementary number theory. Crypto system is called RSA algorithm. The name is an acronym of names of US, Shamir, and Adnan. They invented this algorithm in the second half of 70s, and they patented it. But they were not the first to discover it. The British mathematician Clifford Cox did it some 4 or 5 years earlier, but he was working for the British government and couldn't publish it. It was kept secret. So the base is the modular arithmetic modular product of two primes, two different primes. So let's call them P and Q. And of course the earliest function which controls the cycling behavior of powers modulo this modulus is the product of P minus 1 and Q minus 1. The key fact which is at the base of the whole algorithm is the following generalization of the earliest theorem, which says that any number, any integer raised to this power, it's a shift of 1 by some multiple of the earliest function, will be congruent to the number modulo P times Q. That is similar to the second formulation of the Fermat's theorem, and the proof is by reducing it to modulus P and modulus Q using the Chinese remainder theorem. So if we look what happens modulo P with this power, well, this can be written as W to the first power times W to the power P minus 1. I will single out this and use it as a first exponent, and then I will put everything which is left. So according to Fermat, if W is 0, then that is 0, and of course it will be congruent to 0, which is W. If W is non-zero, then this power is going to be 1, and then that is going to be 1, and I still have W as the answer. So in both cases the product is congruent to W. Modulo P, but modulo Q, the story is absolutely identical. P and Q appear symmetrically in the story, so the answer is W again, modulo Q. So now Chinese remainder theorem says that if we have these two congruencies with the same W, then that must be our remainder modulo the product of two coprime moduli. P and Q are different primes, so they are coprime. Hence we have this fact established, and now we're going to use it. The way we're going to use it is the following. So we have to start by choosing our encryption key. That has to be the number which is coprime, a number which is coprime to the earliest function of P times Q, to this product. So being coprime, we can be sure that there is another number which we will be using as our decryption key, which is the multiplicative inverse of E. So the product will be congruent to 1 modulo the earliest. And written in integers, this equation will become 1 plus some multiple of the earliest function, and the earliest function is P minus 1 and Q minus 1. So that is exactly what we have as the exponent in here. So that guarantees that if we look at this nested power, which is nothing but the product power, and replace it by what it is, then according to this congruence, we will have W back if we are computing modulo P times Q. So that is effectively two processes, raising to the power E, which we're going to use as our encoding process, any message, any word in this message, which for us is going to be a remainder modulo P times Q, encrypted by this operation, by raising it to the power E. So that, let's call it U, that is again some remainder modulo P times Q. Decoding is done by raising this encoded received message to the power D, and because of that congruence, it is going to give us back the original W. So now the arrangement of the CQ algorithm. The public knowledge consists of course, the modulus, the base for the whole arithmetic computations, and the encryption power. So everyone now knows how to take whatever message is to be sent and to raise it to this power and reduce modulo P times Q. And then that is this U which is sent across whatever the communication channel, open communication channel, and then the algorithm master receive this message, and what he or she needs to know is this power D. So this is kept secret. Well, why this scheme is secure? After all, D is uniquely determined by E. It's the inverse, multiplicative inverse modulus modulus. The security of the algorithm is based by the inaccessibility of this modulus, because everyone knows the product of P and Q, but it's very hard to get the factors which are necessary for knowing the modulus. So this factorization problem for large numbers, for two very large prime numbers, is very hard, and that's why the algorithm works. So in the next video we will have a concrete numerical example of how it works. See you later.